Adsorption temperature. The effect of temperature on fluoride adsorption onto soil surfaces arise from its influence on the adsorption energy balance, on the kinetics of adsorbent particles, and on the chemical activation of reacting species. Higher temperatures enhance increased rates of adsorption by enhancement of faster solute transport from the bulk solution towards the adsorbent surfaces. Higher temperatures also raise the average energy of the particles, allowing a higher number of particles to attain necessary activation energy to enable them to react. Very high temperatures may, however, counter the adsorption fluxes, leading to reduced rates and magnitude of uptake of the adsorbent by the adsorbents. As for the effects of solution pH, however, the effect of temperature on fluoride adsorption on popular soil adsorbents is varied. The peak fluoride adsorption by natural montmorillonites, Fe3 modified montmorillonite, pumice and lignite occur within a range of temperatures close to room temperature, 298 K. Nevertheless, the highest fluoride uptake by both aniline modified montmorillonites and pyrrole modified montmorillonites as well as by coal is favored by above room temperatures close to 303 K. It has been found that fluoride-exchange reactions for hydroxyapatites and for certain ferric oxide minerals such as hematite can occur over a wide range of temperatures of 298 to 323 K. Fluoride adsorption onto Mg2+ and Al3+, Fe3+ and 02+ loaded palygorskite minerals, synthetic hydroxyapatites, calcareous minerals and onto magnesia-loaded fly ash cenospheres, MLC, is favored by higher temperatures in the range of 303 to 323 K. This indicates the existence of endothermic chemical surface reactions. The efficacies of bauxite to sorb fluoride has, however, been found to decrease with increasing temperature, indicating the existence of exothermic fluoride immobilization in bauxite surfaces. Contact time. The resident time required for equilibration in an adsorption process depends mainly on the adsorbent structure and on the nature of reactions that occur between the adsorbent particles and reactive sites at the adsorbent surface. Adsorbents with compact crystalline structures and characteristically surface-exposed reactive sites tend to have rapid rates of adsorption than porous media with intraparticle sorptive sites. This is because in the latter case, the adsorbent particles have to be transported by diffusion into the inner adsorbent structures in order to access the reactive adsorbent sites. Fluoride adsorption onto pulverized crystalline calcareous minerals tends to occur rapidly by surface precipitation of fluorite, CF2, over the entire mineral surface. Water defluoridation using calcareous materials is, as a result, normally characterized by fast adsorption rates, and the adsorption equilibrium lies within the range of 30 to 60 minutes. In less crystalline adsorbents such as lignite, more than 90% fluoride adsorption occurs within the initial 10 minutes. It, however, takes up to 150 minutes to saturate the less exposed sites inside the adsorbent structure with the latter 10% of the process. Such trends are also observed in the case of fluoride adsorption onto coal, with shorter equilibration periods of 60 to 90 minutes for the latter phase of adsorption, which shows that coal is more crystalline and less porous than lignite. Equilibration periods required for fluoride adsorption onto pumice have been reported to lie within the range of 20 to 30 minutes, but pumice adsorbents have not generally been associated with the two-phase adsorption phenomenon. This indicates the presence of limited porosity in the mineral structure of these adsorbents. Although some authors have linked fluoride adsorption onto natural montmorillonites to rapid sorption rates associated with the short adsorption equilibrium periods of just 20 to 30 minutes, several natural montmorillonites and Fe3 modified montmorillonites appear to have consistent fluoride adsorption equilibrium time intervals in the range of 110 to 180 minutes. In the same way, a number of mineral adsorbents including metal intercalated palygorskites and certain aluminum oxide minerals appear to have equilibrium intervals within the same range of periods. This signifies that these minerals possess structural porosities that are comparable. As in the case of fluoride adsorption onto calcareous and carbonaceous soil adsorbents, the immobilization of fluoride into adsorbent zeolites, hydroxyapatites, iron oxide minerals as well as into certain classes of aluminum oxide minerals is characterized by initial rapid phases of adsorption characterized typically by short equilibration intervals of just 10 to 30 minutes, which are then followed by prolonged equilibration that could extend to 10 to 48 hours. The final slow phase of equilibration can be ascribed to high structural porosity as in the case of zeolites, or to slow valence exchange reaction mechanisms characteristic of fluoride immobilization upon hydroxyapatite, hydroxide aluminum and iron minerals.